In this video, we're going to introduce propositional logic and we're going to learn how to translate English sentences into logical formulas. So in the next video, in the solution video, we're going to go through these 4 questions. So if you can do them, post your answers below and you'll find the answer within 24 hours after this video is released. But let's begin. What is propositional logic? Propositional logic is all about propositions. Now, a proposition you can think of as a simple sentence. So something like, the sky is blue, or the dog is here, or everywhere is beautiful. A proposition is anything that can be true or false, and some textbooks use a T and an F to represent true or false, while other textbooks use 1 and 0. I'm using 1 and 0 because there are some nice mathematical ways to do truth tables later with the numbers 1 and 0 that you cannot do with T's and F's. So here's some more examples of propositions. The sky is blue during a cloudless day. So for the most part, this happens to be a true statement, provided that there's no smoke in the air or any environmental hazards. The sky on Earth is blue when the day is cloudless. Here's another proposition. 2 plus 2 is 4. Yes, this is a true statement. I'll give it a 1. It's true. 2 plus 2 is 4. Okay, in your standard arithmetic, that is base 10. The sun is a moon. Oh, this is another proposition, but it's false because the sun is not a moon. A sun is the star. So typically, we would give each proposition its own capital letter. So the sky is blue during a cloudless day, we might call this S. And S just means that sentence. So whenever we see S, that's what we read. For 2 plus 2 is 4, I can give this an arbitrary capital letter. Maybe I'll call this A for addition. So anytime we see A, we would think, oh, 2 plus 2 is 4. The sun is a moon, I might call that M. Although the proposition is false, I could still call this M for the moon. Now, these capital letters can be arbitrary and they're going to depend on whatever problem you have, but that's typical convention. So what is not a proposition? What is not a proposition? Well, things that are not propositions are questions. So if you have a question, where are you? Well, that can't be true or false. That's a question. Or you might have, say, a command like, get me a drink. Well, that's not a proposition because that can't be true or false. In order for something to be a proposition, you have to be able to say that's true or that's false. Okay, so let's take a look at some connectives. Now, every proposition is affirmative. So the sky is blue, 2 plus 2 is 4. But we can join propositions together, like the sky is blue and 2 plus 2 is 4, or the sky is blue or 2 plus 2 is 4, or we can just negate one. So we could do the sky is not blue, or 2 plus 2 is not 4. And we do these things called connectives. So not, and, or, if then, if and only if. So these are our conjunctions in the English language, or negations. And we're going to go through each of these piece by piece and show some examples of English sentences where they're used. So we're going to start with the negation, then we're going to do and, or, if then, and then if and only if. So the first one, negation. This is called a unary operator, which means it attaches to one proposition. So if you have P, you can make it not P. If you have not S, you can make that not S. So this just means not. So imagine I have this sentence, Steve will marry a loving person. And I want to call this S for Steve. Okay, let's do that. Let's call that S. What if we now have a sentence, Steve will not marry a loving person? So this not is an operator. This is your negation. So this is where the symbol not comes in. So we could call this not S. That's how we could symbolize that. We could also say, it is not true that Steve will marry a loving person. And this is the same thing. This would be not S. It is not true is another way of saying not. So this is how the not operation works, or the negation operation. And what I should say is that this is not the only way that you see this. Sometimes you'll see this as a little squiggle. So this might be not S. I think formally that's called a tilde, but I like to use the word squiggle. So that's another way you might see not. Some textbooks, if you're looking at set theory or discrete math, sometimes they borrow this notation for logic, but it is very rare. They might use S with a bar over it or S with a little tick after it to mean not. But those two are very rare, and you'll rarely see them in logic. But that is something that could happen. So I show you those just so you're aware that those things can happen. What if we had this sentence, dogs aren't people, and we want to symbolize that? Well, first we have to get the proposition, and the proposition is always affirmative. So the proposition would be D, dogs are people. And in fact, maybe I should do this in a different color. I should do this in white. So call that D. So that represents dogs are people. Now to get the negation in that not, I'll put this in red. So this is where we use the not operator to get not D. So if you have the sentence dogs aren't people, you'd symbolize this as not D because all of your propositions should be in the affirmative, and then you use the negation to represent that not. So that's our only unary operator in propositional logic. The next operator we have is the conjunction, and this means and. There are many different words in English that mean and. So you have and, yet, although, so, even though, because in some cases. So this is a binary operator, and this conjoins two propositions. So binary, the bi here meaning two. So for instance, if you have a proposition P and you have a proposition Q, you can join them together with and. So before we get into translating these sentences, you might also see this written as P and Q with the and sign, the ampersand, or you might also see it with the dot, so P dot Q meaning and. Personally, I prefer this thing called the caret, which is like a triangle without a base, just because that is how I initially learned it, and it is very common in computing science to also see that. So in discrete math, which borrows a lot of logic, you'll see that same symbol. So here's some sentences. Stacy loves milk, and Derek loves chocolate. Okay, so in this case, I'm going to give each proposition its own letter. So Stacy loves milk, I'm going to call this S for Stacy, and Derek loves chocolate, I'm going to call this D for Derek. So this connective and, this is where we use our and sign. So we can conjoin these two, and we would call this S and D. Okay, there's our first example. The second example, I went to the store even though the store was closed. So let's take a look for our simple sentences. First we have, I went to the store. So I'm going to call this W for went, even though the store was closed. So our second simple sentence here is the store was closed. So I'm going to call this C for closed. Now what I have in the middle is this even though, and even though is like although. So this has different meaning when it comes to conversational expectations, but in terms of whether something is true or not, this is very similar to the word and. So this is just another way of expressing and in logic. So this is also a caret here. So we could translate the sentence as W and C. So I went to the store even though the store was closed. That is the same thing as saying I went to the store and the store was closed. Next example. Although Ben is tired, he still wakes up on time for school. So let's find our simple sentences. Ben is tired. This is one. So I'm going to call this T for tired. He still wakes up on time for school. Okay, that's another simple sentence. I'm going to call this one W for waking up. So where's our operator here? We have T, we have W. Well, we have although out front, so our and is out front. So you might be thinking, how do we symbolize this? Well, we can paraphrase this. We could say, Ben is tired, although he still wakes up on time for school. So even though although is out front, we could still paraphrase it and put it in the middle. So we can translate this sentence as T and W. Ben is tired, and he still wakes up on time for school. Okay, finally, let's do this last sentence. Both Azad and Omar were able to cook a delicious meal. Now here we have something hidden. We have both and. So we have our and operator here, but where are our two simple sentences? We have Omar was able to cook a delicious meal, let's call this O, but we also secretly have this Azad was able to cook a delicious meal, A. Now the key here is that we could break this up into two sentences. We could say both Azad was able to cook a delicious meal and Omar was able to cook a delicious meal. We've just elided a little bit here. So elided means that we just haven't pronounced the remainder of that first sentence. So we could translate this as A and O. So Azad was able to cook a delicious meal, and Omar was able to cook a delicious meal. Now, here's one final question for you. And I'm actually going to get rid of this stuff so we can focus on this question. So, of course, you can look back at the answers by pausing the video and looking at that. But I'm going to ask you, is this a sentence with a conjunction? Tracy and Carla are sisters. Well, if this is a conjoined sentence, what that means is that we would be able to split this up into two separate sentences. So can we say Tracy is a sister and Carla is a sister? Well, you can, but does it have the same meaning as Tracy and Carla are sisters? The answer really here is no. This is just one proposition. You could just call this S for sisters. And that's because if you break this up into two separate sentences, Tracy is a sister and Carla is a sister, it does not have the same meaning that Tracy and Carla are sisters to each other. So not every time you see and is it a conjunction. You have to ask yourself, can I split this up into two different sentences and have those sentences carry exactly the same meaning as what we have here? So that's just one sort of tricky example. Okay, now we have the disjunction. This means or, it's another binary operator. So typically you see this called the wedge. So you'd have, say, something like P or Q, but you might see this with a plus sign, so P plus Q. And that's something you would see often in, say, digital logic, which we're also going to cover in this series. So let's see some examples here. Either I leave or you leave. Okay, so I leave, let's call this I for the simple proposition I leave, or you leave, let's call this Y for you leave. And our operator here is or. We see here, either or contributes to the same thing. So this is or, so we can translate this as I or Y, or I leave or you leave. Here's another example. I will leave unless you leave. So let's call I will leave I again. Let's call you leave Y again. Now, unless has the same meaning as or. Now, a lot of people think about unless in terms of like an if-then or in terms of the conditional, but it's easier just to express it as an or. So this might not be intuitive at first, but this is one of those tricky words that often comes up in assignments or tests in university courses on logic that can be simplified if you just use an or. So this can also be translated as I or Y. So I will leave unless you leave. It's the same thing as I will leave or you leave. Because what this means is I will leave unless you leave. So I will leave if you don't leave, or if you do leave, then I won't leave. Let's just move on to the next example. Tracy likes rabbits. Tracy likes rabbits, or she doesn't like rabbits. So Tracy likes rabbits. Let's call this T. Or she doesn't like rabbits. Oh, look here. I have an nt here. So I have a not in this case. So not T over here for Tracy doesn't like rabbits. And I also have or here, which is our operator. So we can translate this one as T or not T. Tracy likes rabbits or she doesn't like rabbits. Specifically, I could say Tracy likes rabbits or Tracy doesn't like rabbits. Finally, neither Bill nor Ben found the hidden amulet. So here we have neither nor. We'll talk about how to deal with this in a second. But we have Ben found the hidden amulet. So I'm going to call this B2 for the second name that starts with a B. And I'm going to say Bill found the hidden amulet as B1. Now let's think about the meaning of this. How can we paraphrase this? Well, Bill didn't find the hidden amulet, and Ben didn't find the hidden amulet. So one way I could translate this would be not B1 and not B2. But I want to translate this with or. So neither Bill nor Ben found the hidden amulet. How I can think about this is I can say, Ben found the hidden amulet or Bill found the hidden amulet. But in reality, neither of them did. So how I could translate this is not B1 or B2. And there's actually two ways of doing this. So not B1 or B2, or you could think of it as not B1 and not B2. Now these are both equivalent. These both mean exactly the same thing. It's just two different ways to translate neither nor. So when you see neither nor, you have two different ways of translating that. Okay, the next one is the conditional. The conditional is another binary operator. So you'd see something like P arrow Q. Sometimes you'll see this with this horseshoe pointing open to the left. So PQ, that's called the material implication or the material conditional. I like to use the arrow because if then with the arrow, it's just intuitive to me because it's like an arrow. If this first thing happens, then something else happens. And there are terms for what is on the left or what is on the right. So the thing on the left, the if part, is called the antecedent. So that's the condition that has to be met. The thing on the right, so the thing in the then part, is called the consequent. So that's what happens if the antecedent is true. So let's take a look at some examples. First one, if you leave, so call this y, I will not be happy. So we'll pick H for happy, and we'll put the negation in front because of this word not. So the question is, which one comes first? Is it y arrow not H, or is it not H arrow y? Well, the if is out front here. So if you leave, this means that this y, this is the antecedent. So that's the condition. And then I will not be happy. That means that this not H, this is the consequent. So this is what happens if you leave. So that means that we can translate this as if y, then not H. So if you leave, then I will not be happy. Okay, next one. The sky will turn red. Let's call this S if there is a lot of smoke. Okay, I'm going to actually change my label for this. I'm going to call that R for red, and there is a lot of smoke. I'll call that S. Now, here, if is in the middle. So what is the antecedent? Well, whatever comes after if in this case, if there's a lot of smoke. So here, S is the antecedent, and the consequent, what happens if the antecedent is true, would be R. So if there is a lot of smoke, then the sky will turn red. So we can translate this one as S arrow R. So if there is a lot of smoke, then the sky will turn red. You could just paraphrase this too and put the if out front. Okay, here's another one. We will dance, let's call that D, provided that you learn some dance moves, let's call that L. So where's our if here? Well, provided that is like another word for if. Because provided that sets up a condition. It sets up an antecedent. What is the condition that has to be met? Well, if you learn some dance moves, then we will dance. So that means that L here is our antecedent because the condition word is provided that. And that also means that we will dance is going to be our consequent. So how we can translate this is if you learn some dance moves, so if L, then we will dance. So L arrow D. Okay, finally, the pencil will run out of lead when you finish writing your paper. So the pencil will run out of lead. Let's call this L. You finish writing your paper. Let's call this W for writing. And what about this word when? Well, again, when is another condition. Whatever comes after when is the condition. That means that W is our antecedent here. It is the condition. And the pencil will run out of lead is the consequent. So when the condition is met, this will happen. The pencil will run out of lead. So we can translate this one as if W, then L. So W arrow L. So this is how we can translate the conditional. Now the conditional can sometimes be tricky, so there'll be a separate video on how that works a little bit later. We'll learn about terms like inverse, converse, and contrapositive, as well as taking a look at words like is necessary and is sufficient. The last thing we're going to learn today is the biconditional. This stands for if and only if. So the biconditional P if and only if Q is really just the conditional in both directions. So if P then Q and if Q then P. You might also see this written as 3 bars for equivalence, but I like to use the double arrow because when you have a double arrow, it works fantastically with the arrow notation because you know it's just an arrow going in both directions. So P arrow Q and Q arrow P. So let's do our last 3 examples in the video. You will become rich. This is nice. Let's call this one R. If you get lucky, that's W, or let's call this a W, that's L. And if you work hard, so that's W. So really here we have a conjunction because we have this word and in the middle. So you will become rich if and only if you get lucky and work hard. So what's nice about if and only if is that we don't have to worry about the direction. We can just translate that as a biconditional right away. So we can translate this overall as R if and only if, L and W. So you'll become rich if and only if you get lucky and work hard. So you get lucky and work hard is in brackets because both of those things have to happen on one side. Remember, a biconditional, like the conditional, like the conjunction, it's a binary operator. It needs two propositions. So R is one of our well-formed propositions, and L and W is another one of our well-formed propositions. So it can only have essentially one unit on each side. So by putting the brackets around L and W, we make that one unit to use this biconditional operator. In the next video, syntax, of propositional logic, we're going to cover more about what that means. Okay, being an even number, so let's call this E, is necessary and sufficient. This is like saying if and only if, so we have our biconditional here, and condition is part of that too, for being divisible by 2. Let's call that D for divisible by 2. So this is a simple one to translate. This is just E if and only if D. So you are an even number if and only if you are divisible by 2. That's another way of paraphrasing that. Finally, I will bring an umbrella when and only when it rains. So I will bring an umbrella. Let's call that U for umbrella. And it rains. Let's call that R for rains. Now, when and only when, you remember when is another word for if. So when and only when is the same thing as if and only if. We can represent that with the bicondition. So we can translate that as U if and only if R. I will bring an umbrella if and only if it rains. So those are the 5 basic operators of propositional logic, and we translated a lot of sentences in this video. So what I want you to do is I want you to try to translate the sentences you saw at the beginning of the video here. And within 24 hours, we're going to have the solutions posted, so you can check them then. And if you have any further questions, you can always ask in the comments, and I'll try to get to you when I can.